we'll start with more of the number stuff and then move from there into chemistry. Data and so we have the average, abbreviated X bar. So, good. Here for chemistry? Perfect. Is there anything in particular that you found challenging this week? Okay, works for me. Your average is X bar, and that is going to be the sum of your values, sum of X, that's sigma sum, divided by n. Where n is your number of n. Then you have your standard deviation. So we use standard deviation to characterize how tightly our data is arranged. So if our data looks like this, if we graph it, that has a high standard deviation compared to if our data looks like this. If you guys covered accuracy and precision, what could you say about these two graphs using those terms? Is one of them more accurate than the other? Is one of them more precise than the other? Any ideas? We can't actually tell the accuracy off of this without knowing the true value. Right, if I told you, here's your graph, this is the true value, and that was your data, then we could. All we know is that this is less precise and this is more precise. Does that make sense? Our standard deviation is calculated one of two ways. We can say the standard deviation is equal to square root of the sum of x minus x squared divided by n minus 1. You also see it as the square root of the sum of r minus x squared over n. So, when do we use which one? With this, I would have you guys ask Dr. Martin which one she wants to use. You won't be calculating this by hand. She covers it more to cover the theory of it. This is used with examples. So n should be less than 30, and this is with population. N greater than 30. This distinction is more important in the social sciences. So if you're doing measurements of people, that sort of thing. But it would be worth asking her which one she wants to do, or reference your notes for what she had written down as the formula. Any questions on this? You want to go through calculating standard deviation? Okay. Let's say we have three values, 3, 5, and 4. And we'll do this one. So this would be our x. What is our average? Four. So paper, it's easy to do sort of chart work of it. So we have our x and our x bar. Our next step is the mean minus the value. So 4 minus 3 gives us 1. 4 minus 5 gives us a negative 1. 4 minus 4 gives us 0. Now, the reason why we have this formula where we square these things and then square root them is because if we just add those up together, we get 0, which is what we should get, because these are equally spaced out around the mean. So it doesn't matter what your values are. Once you determine your mean, if you were to add up mean minus x, you'll always get 0. Get x squared. So 1 squared is 1, negative 1 squared is 1, 0 squared is 0. And then we're going to add them together. So there's our sigma. So that means to add them up, we get 2. So then 2 divided by n. What is our n here? 3. 2 divided by 3, I'm going to take the square root of it. So our standard deviation would be the square root of 2/3. Anyone have any questions on that? Great. Do a few examples of significant figures. Right? If I have 100.34, how many sig figs is that? 5. What if I have 0.0012? 2. What if I've got 10.01? 4. Does that make sense? Right? That's 4. What if I've got 600 with a decimal? 3. What if I have 6.2 times 10 to the 15? 0.000001. 1. What if I take 16.0 plus 1.9342? What am I going to get my answer at? Great. I've got 3 6 here, and I've got 5 6 here. And when you add and subtract, we're going to use the fewer number of significant figures. So in this case, the arithmetic answer might be 17.9342. So we're only going to use 3 figs, so we're going to say this is 17.9. We don't have to round here. We'll round down. Does that make sense? What if I have 15.00 times 2 divided by 4.00 plus 19.341? mixing thing. For multiplication, what do we use for our sig figs for multiplication? I'm sorry. Back up a bit. So here's your addition and subtraction. How do we determine sig figs for addition and subtraction? Right. How many decimals do you have? So in this case, we have 1 decimal. Sorry to go back there. Here we have 1 decimal, and here we have 4 decimals. So we're going to report our answer to the lowest number of decimals, which in this case is 1, so you still have 17.9. Yes, it just happened that this example worked out both ways. Yeah, I just got lucky. Yes. Yes. Yep. Does that make sense? Okay. So we'll do one more example here. You have 0.0001 plus 1.0. What's my answer? 1.0. Now down to here. So multiplication and division, we use the lowest number of sig figs. So here we have 4 sig figs. Here we have 1. So what answer do we have for this problem? So when you're mixing things, we're going to want to use our order of operations and take one thing at a time. But what's important here is that we carry all of our values through, even if they're not significant. I'll show you what that means. What's 16 times 2? 32. But we can only have 1 sig fig. So what does that mean that this number is 30? Working with these numbers, note what it is and how many sig figs it has. But as we go through, you're going to want to carry 32. We're not going to change the number to 30. Just know that you only have 1 significant figure right now. What I find useful is mark it in some way that you know that you're only significant to that 32. Does that make sense? Now we divide by 4. This has 3 sig figs. This has 1. We know our answer is only going to have 1 significant figure. But rather than take 30 divided by 4, we take 32 divided by 4. What do we get? 8. And this is our only significant figure. So then when we take 8 plus 19.341, what would we say our final answer is? No? So if we do the math, we get 27.341. We're adding and subtracting, so we default to the lowest number of decimals. How many decimals does the 8 have? 19.341 times 3. So our answer is going to be the fewest number of decimals, which is 0. So our answer here is 27. Does that make sense? I apologize if I confused you with the first example here. Any questions on sig figs or data analysis? Cool. Let's do an example of unit conversion. You guys have the practice there, and then we'll get into more of the meat of the chemistry that you guys have. 3.0 grams of sodium phosphate in a week. You have to know what the formula is for that. I'll give it to you as Na3PO4. You guys have not gotten polyatomic ions yet. You would know if you did, which should be probably early next week. So Na3PO4. How many atoms of oxygen do I have? You guys haven't gotten to the chemistry with it, but nonetheless, through the methods that you know for your unit conversions, you still know how to solve it. I'll give you a couple values here that you probably don't have any idea. So 1 mole is 6.022 times 10 to the 23rd atom. What's this number? Avogadro's number. And 1 mole of sodium phosphate is 184 grams. Last bit that I want to talk about is, so I have atoms of oxygen. So how many atoms of oxygen are in 1 atom of sodium phosphate? Anybody want to take a guess? We've got Na3PO4. Not a trick question. Four. So with these conversion factors, I want you guys to try to work through the conversion of 3 grams of sodium phosphate to atoms of oxygen. And not too far, I'm just going to do 3.6. know that you guys can do this, but don't be worried if you're having some difficulty because it is a complex problem. I know that you can, but I wouldn't expect you to be able to get all the way through. You guys ready? Okay. That's where we're going to get our negative answer. So, what unit are we starting with? And what do we need to get to? Atoms of oxygen. Can I go 3 from grams to atoms of oxygen? What can I go to from grams? Can I go from moles of sodium phosphate to atoms of oxygen? Can I go from moles of sodium phosphate to atoms of sodium phosphate? Yeah. Can I go from atoms of sodium phosphate to atoms of oxygen? Does this make sense? So far? So starting at, we're going to get to stuff along the way. So if I start with 3.68 grams, I call this NB. 3.68 grams of sodium phosphate. What do I need to put in the denominator here? So what unit do we want to end up with? After we're done with this step here. Moles of what? Moles of sodium phosphate. And we want to cancel our grams. Does that make sense? So grams cancel, we'll be left with moles of sodium phosphate. And what's our conversion for this? Well, 184 grams to 1 mole. That's what this conversion factor right here. So now our grams of sodium phosphate would cancel. We're just left with moles of sodium phosphate. And we're going to go from moles of sodium phosphate to atoms of sodium phosphate. And what you'll find is that we can actually do these steps interchangeably. Put 1 mole on the bottom. That cancels. We're going to go 6.022 times 10 to the 23rd atom. That's atoms of sodium phosphate. So what am I going to put in the fourth? There you go. So we've got atoms of sodium phosphate. We need to get to atoms of oxygen. So what do we need to cancel? Atoms of what? And what do we want to end up with? Atoms of oxygen. And what's our conversion? 4 atoms of oxygen for every atom of sodium. What questions do you have here? Does this make sense? Alex? So if you had one compound of sodium phosphate, then you would have 4 atoms. Right? That's what this conversion is here. So we don't know how many compounds of sodium phosphate that we have, but we do know. That's a compound. We do know how many grams, and we know how to go from grams to units of sodium phosphate from our conversion here, and that's with the molar mass. You guys will get through hopefully soon. That's what I was calculating over there. And then once we get to moles of that, then we know how to go from moles to atoms. So it's just one step at a time. And then I picked numbers that would work out nicely. Did somebody calculate it? Should be some factor of this. Don't worry. Okay. Sig figs are great. Learn about them, know them, care about them, and then you just have it. If you're a chemistry major, you'll see them in quant. Beyond that, it's still very similar. Know your sig figs and then move on from them. It's important for data and producing data and publishing. But when you're asked in this class, if you're asked a question that's related to sig figs, do your sig figs. If you're asked a question that has nothing to do with sig figs, don't worry about it unless you get answers that are all very close. So if you have like A is 3.6 and B is 3.61, then you know that you need to do your sig figs. For the most part, don't worry about it. The final exam in this course is a standardized test produced by the American Chemical Society, an ACS test. They designed that test to test one concept per question. So rather than having a question that covers sig figs and unit conversion, so that's a question on sig figs and question on unit conversion. Why? Because they want to make sure that when they analyze the data, if there's a question on sig figs and unit conversion, they don't know if you got it wrong because you didn't know sig figs or because you didn't know your unit conversion. So they want to be able to take a look at that. So don't worry about it. All right. That gives you 0.05. Anyway, you back up to there. Any questions on this? Any other questions on unit conversion? Yes, I think most of if you want to do any other conversion. The only thing this didn't cover is converting between prefixes. So we just had grams, we just got kilograms, so kilograms per grams per your time conversion. You get there. Compound. Compounds are two or more atoms bound together. have molecular compounds. Or molecules. And we have ionic compounds. Molecular compounds are formed with covalent bonds. Whereas ionic compounds are formed with ionic bonds. Covalent bonds are sharing of electrons. Whereas ionic bonds are donation and acceptance of electrons. And all bonds are sharing of 2 electrons. Thank you sharing both ways for you guys. This isn't much sharing, but it involves sharing 2 electrons. Yep. So all bonds use 2 electrons. So the molecular formula shows the actual quantity of atoms, whereas ionic formula shows the ratio of atoms. That is more of what that means. Some terms to know for ionic compounds: you have a cation with an anion. Anybody want to take a stab at what a cation is versus an anion? Cation is your positively charged species. Anion is what? Negative charge. Couple memory tricks. Cation has a T. A T looks like a plus. Cation is positive charge. Cation has cats in it, and cats are positive. Anion. Anything that starts with an in English language normally is the opposite, negative or removing, like anti and antithesis. Anything else, an is normally negative. Any questions with this stuff? Which we probably done with this. That is a term that is used to describe you'll see it commonly as in chemistry as either an atom or an ion. We haven't seen it yet, but get used to seeing it and remove it from the biology box of your brain. Basically, just positively charged thing. molecule are going to be two nonmetals, and ionic compound will be a metal with a nonmetal. Okay. Yes, two nonmetals and ionic compounds are metals. So, this is the periodic table. All of these are metals. These in yellow are your nonmetals. Once you get more into the periodic trends, do this one step further. But an example of a molecule is CH4. This is methane. You don't need to know that here. We have methane, this is CH4. What this means is that we have carbon bound to hydrogen. C3H. Propane. So what this means, I'll go back to my thing. Oh, explain why I wanted to. So this means we have one carbon bound to four hydrogen. So, because it's a covalent compound, this is the equal sharing of electrons. You can determine the number of electrons in an atom's valence shell, what that means is the outer electron shell, by its placement on the periodic table. So, these elements in the first column, for the first group, have one electron in their valence shell. The second column has two electrons. You skip everything in the middle, 3 electrons, 4, 5, 6, 7. Atoms are stable with 8 electrons in their valence shell. That's why these noble gases are inert and non-reactive. Hydrogen has 1. Almost all of your compounds want 8 in the valence shell. Hydrogen and helium want 2. Without getting too specific, your first shell contains 2. The shells thereafter contain 8. So we want that shell to be full. Hydrogen and helium want 2. Carbon over here in the 1, 2, 3, 4 group that moves here in the fourth group. That means it has 4 electrons in it now. You have carbon, which has 4, wants 8. Hydrogen has 1 and wants 2. So when these come together, they end up sharing these electrons in that bond. All 4 hydrogens get their 2 electrons, and carbon gets total 8. That's what we have here. Does that make sense? It's equal sharing of electrons. Part of why, in this case, it's an equal sharing is carbon has 4, it needs 4, so it's got half of as many as it needs. Hydrogen has 1, it needs 1, so it also has half as many. So they're not, neither species is considerably more electronegative. We'll talk about electronegativity probably in a couple weeks here. So basically, neither one of them wants the electron more than the other. Does that make sense? Okay. Ionic compounds, let's use sodium chloride, NaCl. How many electrons does sodium have in its outside shell? One. In that first group. How many electrons does chlorine have? 7. We know that sodium is a metal and chlorine is a nonmetal. So, we have a metal and a nonmetal. We know we're dealing with an ionic compound. Chlorine is really, really, really close to having 8. So it really wants this electron. Sodium has 1 electron, but what you don't see is because we have electrons in shells. So we talked about, so sodium is atomic number 11. 11. What does that mean? I'm outside of my frame. That's why I do that one. Sodium is atomic number 11. How many protons does sodium have? How many protons does sodium have? 11. It's atomic number 11. The atomic number tells us how many protons. We're going to say that this particular sodium has a mass of 23. How many neutrons does this sodium atom have? Cool. Because we know our protons and our neutrons are the only 2 components that contribute to our atomic mass of 23. So 11 plus 12 gives us our 23. How many electrons, assuming the sodium is neutral? What's the charge on an electron? -1. What's the charge on a proton? +1. If we have 11 pluses, how many minuses do we need to get to 0? 11. We have 11 protons and 11 electrons. So this sodium has 1 electron in its outer shell. I said that your first shell has 2. Every shell thereafter has 8. So if I have 2 electrons in my inner shell and 8 electrons in my shell, my third shell, I know has 1. And so we get to 11. So what's going to happen if sodium gives up that 1 electron? How many electrons remain in its outer shell? None or 8. If sodium gives up this electron, that's the only electron in that shell. Now its outer shell has 8 electrons, which is stable. So just as much as chlorine has an attraction for that electron, sodium wants it gone. So what happens here is that this electron actually gets transferred over to the chlorine atom and becomes chloride. I'll talk about naming. No, we'll talk about naming. So that becomes chlorine with a negative charge because we added an electron. We didn't add any positive charges or any protons to counteract it, but we added a negative charge. Sodium gave up that. It would have a positive charge. We have sodium, a sodium ion, and a chloride ion. One is positively charged, the other is negatively charged. Just like magnets, they'll be attracted to one another. We end up with Na. Now, unlike molecular compounds that have discrete bonds, ionic compounds are ratios of charged particles. So, carbon is actually bound to 4 hydrogens, and hypothetically we could remove 1 molecule. Ionic compounds exist more as a lattice structure of things attracted to one another. If you have let's say a bunch of magnetic balls. You have some large magnetic balls and small ones, and you put them all in the bin, and they all attract to one another. That's more of an ionic compound. So there's no discrete bonds necessarily. There's just a general attraction. Because of that, we show ionic compounds as the most simplified form. Let's say we have, we'll go back to our previous example of sodium phosphate, NH2O4. What we talk about this upcoming week is that phosphate has a negative 3 charge, and sodium, when it becomes an ion, has a positive 1 charge. That's why we need 3 of them to make this neutral. But this is just a ratio. We have 3 sodium to 1 phosphate. Likewise, if we had 6 sodium, we would have 2 phosphate, but we would never draw that out in the ionic form. Whereas in the molecular formula, I could have CH4, but I could also have C2H. I have C2H4. I can also have C4H8. These are different molecules, they're different compounds. Even though the ratio of carbon to hydrogen is 1 to 2 in both cases, it doesn't have discrete bonds, there's different compounds, unlike with the ionic compound. Does that make sense? So this would be, I'm getting too specific into chemistry, you would have this molecule, which if we could isolate, we could pull out that molecule. Whereas this here, would look like this. So it's a different molecule. Does that make sense? Yes, no, any questions on this stuff? Any questions before we close today? This is fun. Anything else you want to touch on before we finish up? When is your first exam? No. Online. Next week, we will likely talk about polyatomic ions. That will be when you guys get to it. Tuesday. That will likely be the big topic of chapter 2. And initially, it's confusing. Once you get the hang of it, then it's pretty self-explanatory. Some of the examples that we did, you'd be able to see without any effort. For your timeline. If you guys need anything, this is my email. Shoot me an email. Or just H-O-O-S-E. Moose with an H. I am recording all